Hello, I'm David. I'm one of the lecturers in the Maths Learning Centre at the University of Adelaide, and this is a bit of a rough and ready lecture on exponentials and logarithms. Okay. So the theme of this lecture is going to be the sorts of things that we need to do to make sense of functions and notations. So we're going to be introducing a couple of new kinds of notation and a couple of new functions, and there's going to be some questions that we should ask about them in order to make sense of them. And we're going to run through all of them. Okay? So, and I'm going to list them now so that we know where we're going. So, the questions that we need to ask are, what does it mean? Like, how do you do it? What is it? And since it's a function, we should know what its graph is like. And we should know what rules there are for working with it. So how does it interact with plus and minus times divide, those sorts of things. So what rules are there for working with it? And in particular, we should do some calculus. So what are some? So how does derivative work? So actually, this has two sort of what rules are there for working with it, and it has sort of two subheadings. One is just algebra. And the other is calculus. Okay. And then we should know sort of what situations does it appear? What's it used for? Okay. So these are some questions that we're going to ask. And we're going to find some answers to most of these to all of those questions. Okay, so it's going to take me a little while to get a handle on this, and then we can start looking at the graphs. And I might sort of do these two things together. They're all going to be mixed together a little bit, but we will know when the answers have been given. So let's have a look at what is it. Okay, it's going to take me a little while even to say their names. So what we're going to do is we're going to have this sort of a pattern that's going to be growing by multiplying by something each time. And so we're going to have, because functions are a little bit like that, you stick some numbers in and some numbers spit out, and you can create those functions in lots of different ways. And our function is going to be created by continuously multiplying by stuff. So let's see. So what if I started with, say, I don't know, 2? And then I kept multiplying by 2 over and over. So the third time I'll multiply by 2 again. The fourth time I'll multiply by 2 again. The fifth time I'll multiply by 2 again. The sixth time I'll multiply by 2 again, and so on. Okay, and that's an idea. And we could go back a step from there and start out with a 1. So I started at the beginning at time equals 0. Let's say it's time with 1, and I keep multiplying by 2 as I go. This process is called, we're making powers of 2, right? We're doing multiplying by 2, and then 2 times 2, 2 times 2 times 2. This is 2 times 2 times 2 times 2. This is 2 times 2 times 2 times 2 times 2. And starting at 1 is an easy way of keeping track of how many 2's we've multiplied since we started. Okay, that's cool. So we could say that the answer here, this is 1 times 2, this is 1 times 2 times 2, this is 1 times 2 times 2 times 2, this is 1 times 2 times 2 times 2 times 2, and we would call this 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. Okay, cool. And these are powers, okay? So the whole thing is called a power of 2. And this thing up the top is called an exponent. And what we've done is we've created a formula where whatever this value here is ends up in the exponent of this. And so it's called an exponential function. Y is equal to 2 to the power of x. Okay, cool. All right, and that's what it is. I mean, that's not all it is, but that's the beginning of it. An exponential function is characterized by the fact that when you move the x up by 1, what you end up by doing is multiplying by something. Okay? So an exponential function has the property that increasing x by 1 multiplies y by the same constant. So no matter where I'm up to, if I increase x by 1, then I multiply x by the same amount. Okay? And that should work actually all the time, that increasing x by the same amount will always multiply by the same constant. So I should just add that in. And that's an idea that we use to fill in the gaps between them. So to get from 1 to 2, I would have to go to 1, get from 0 to 1, I would have to go to a half and then to 1. And increasing by a half should always multiply, increasing the x by a half should always multiply the y by the same number. And so I need to figure out what number that's going to be. So going from 4 to 5, going from 4 to 4.5 should multiply by a number, and then I should multiply by the same number to get to 32. And so in that case, increasing by a half should be multiplying by two numbers that together, when they multiply together, gives 2, which is the square root of 2. So that ultimately produces a rule that we need. I'm just going to do an example here. No, I'm not. I'll get to that later. So all of that reasoning that I just talked about gets the same, can get us to a lot of different rules about how exponentials work. I'm just going to make one more point. To get from 0 to 2, I had to multiply by 4. To get from 2 to 4, I also multiply by 4. From get to 4 to 6, I have to multiply by 4. And in fact, to get from 3 to 5, I multiply by 4. Same thing happens everywhere in an exponential function. It has the property that adding before is multiplying by multiple constants afterwards. Okay, that's an exponential function. And we can make those tiny pieces as small as we like and figure out exactly what we would need to multiply by to get from one place to another. Okay, so let me just do just another example. So we can fill in the gaps between these things by thinking about what we would have to multiply twice by to get to there. So this would be times some constant and then times some constant again. And so therefore m squared, 1 times m should be the same as 1 times 2. And so therefore m should be root 2. And let's just check. Times root 2, we get to root 2. Times root 2 again, well, root 2 times root 2 is 2, correct. Times root 2, we get to 2 root 2. 2 root 2 times root 2 again would be 2 times 2, which is 4. 4 times root 2 is this, and so it works. And you could do that for anything and fill in all the gaps between them and to as fine-grained detail as you like. Okay, that's an exponential function. A logarithmic function is the opposite. So in a logarithmic function, we would like to create a function that instead of adding to the inputs produces multiplying to the outputs, we're going to do something that multiplying the inputs produces adding on the outputs. It's literally going to do the reverse of this. Okay, cool. Before I do that, I'm just going to put a little box under here just to clarify. All exponential functions can be written as f of x is some number times some number to the x for some a and a. Okay. And the classic number to use in this position for little a is the number e, which is about 2.7. Your calculator has it on there. It is here, e to the power of 1. That number, 2.718281828, it does not actually repeat. It looks like it's 1828, 1828, 1828, but it is not. It stops repeating after that. and starts going crazy. So yeah, don't believe that it repeats forever, because it doesn't. Okay? It's common to use e. i.e. f of x is some multiple of e to the x, like that. It doesn't have to be x. It could actually be some multiple of x here. We could have a k there like that, where e is approximately 2.718281828. Okay. And that number will become clear why that number is useful later on. Okay, that's what it is. So what about a logarithmic? What about a logarithm? We talked about an exponential function. What about a logarithm function? Well, a logarithmic function is the reverse. So what if I tried to do this backwards, so that I had multiplication before becomes addition afterwards? So a has the property multiplying x by the same amount adds the same constant to y. So that's a logarithmic function. It's the opposite. In an exponential function, adding before produces multiplying after. In a logarithmic function, multiplying before produces adding after. And you've seen this, and you've seen it for years and years. Watch. If 1 has 1 digit, 10 has 2 digits, 1,000 has 3 digits, sorry, that's 100 has 3 digits, 1,000 has 4 digits, 10,000 has 5 digits. Actually, even better, you used to just count how many zeros there were. 1 has 0 zeros on the end, 2 has 1 zero, 3 has 2 zeros, 100 has 2 zeros, 1,000 has 3 zeros, 10,000 has 4 zeros. And you'll notice when this times is by 10, this goes up by 1. And when this times is by 100, this goes up by 2 every time. That's a logarithmic function. Now, the problem is, this function is not particularly well defined at the moment, because how on earth do you figure out what happens in the middle here? What do you do when you get 2? Well, that's okay, because multiplying by 2 should always add the same amount. If I can figure out how many 2's to multiply to get to 10, oh, that's going to be a problem. All right, but that's not too bad, though, right? How many 2's should I multiply to get to 10? Approximately 3 and a bit. And so I'm going to need to figure out, divide this into 3 and a bit bits. And it'll be sort of about, a little under a third. And so that's how I'm going to do that. Okay? So, yeah. So it's a little easier with other functions. With something where you multiply by 2, it always adds up by 1, because you basically end up filling it in this way. So let me just do one more example. These are called logarithmic functions, and this function here is log on the calculator. This thing here, log. So log of 1, 0, log of 10, 1, log of 100, 2. That's what this function here is called. And so the notation that we use is to do with the number that you need to make it go up by 1. So let me just give one more example. Denoted by that, where b is called the base. And b is chosen multiplying x by b increases the answer by 1. Okay? All right. So let me just look at some stuff that's going on here. I'm going to do log 10. And I'm just going to show you that it really does work with my calculator. In my calculator, log here is log base 10. So if I start with 1 and I start multiplying by, say, 3, then let's see what happens. There's 0.47712. Now if I multiply by 3 again, log 9, 0.95424. Well, just a second. 0.47712. 94. Ooh, interesting. And so if I multiply by 3 again, log 27, it's 1.3136. So let's see, 0.95424 plus 0.47712 is, there we go. So if I add another one of those, 1.90848, I mean approximately, it should get me to 81, right? Yep, there it is. So every time I multiply by 3, I'm adding 0.47712. That's how logarithms work. Multiplying the input by something will always add the same, by the same thing, will always add the same thing to the output. Whereas an exponential function works the other way. So just some special notation. ln x, so i.e. this is a small l and this is a small n, ln x is the logarithm to base e of x. So that means that if you want to increase ln x by 1, you should multiply by the number e. Okay? Log x is log base 10 of x in a calculator. But it will be ln of x in Wolfram alpha. So if you're in the online calculator Wolfram alpha and you see log x, it means ln of x. And it means log 2 of x in computer science usually. So just be careful. It's probably not a good idea to just write log x. Ln x is always safe if you're planning to use it. But if you're doing a log with the word log, you should probably write base, whatever the base is, just to be sure that whoever's reading it can understand. Okay, so what does that mean, David? Well, yes, what does that mean? Well, it does mean a few things. The first thing it means is that logarithmic functions take a very long time to increase. And their graphs tend to turn out a certain way because of that. They tend to be gently, and getting more and more gentle as we go. Whereas exponential functions, because when you add, you end up multiplying the answer, they increase very quickly. And so their graphs will turn out to be certain shapes. So graphs will turn out to be certain shapes. And look, it's going to be easier to get a computer to draw this for me. So let's draw some. That's 2 to the power of x. So you can see here that when x is 2, the y comes out to be 4. When x is 3, the y comes out to be 8. And when x is 4, the y comes out to be 16, and so on. They're the things that I calculated earlier. I might actually just get it to... Okay, so there are the points that we calculated earlier. And we can do it with the root 2's. They're the root 2 ones that we did as well. And we have the ones in between. No. Oh, I see. No, not going to work. Sorry about that. There's some puzzling things going on over this side, though. What does it mean here? Why is it getting smaller on that side? Well, it seems reasonable that if your function multiplies, when you add 1 to the x, should multiply by 2, then when you subtract 1 from the x, it should divide by 2 going backwards. And so it should be that if you start, we know that if we start at 0, we get 1. So if we go back 1, we should divide by 2 to get a half. And if we go back another 1, we should divide by 2 again to get a quarter. And yes, those are the points that are there. So if we go backwards, we should be dividing by 2. If we go forwards, we multiply by 2. And that's why the graph has the shape that it has, because it grows very fast when I'm on this side, and it gets very, very close here because we keep dividing by 2. But no, it does go on forever. It keeps going up and up and up and up. Every function value, it looks like, if you're at 10, that there isn't a function value up there, but there will be if I zoom out far enough. If I go up far enough at 10, I'll find it. It'll just be a long way away. Come on. Getting there, getting there. Oh, we're getting close. We're getting close. Aha, there it is. We've crossed it. It's somewhere in here that it crossed that line. So if I change my y scale to be up to about 1,000, then I can see that here at 10 it crosses at just over 1,000 if I change the scale. It does keep going up, it just keeps going up faster and faster and faster. Okay, that's exponential functions. I'm just going to draw that down. Like that. So if this was y equals something to the x, then this point would be 1. And it would be going very fast on this side and very gently down on this side. This is if the a is greater than 1. If the a is less than 1, we go back to the computer. Watch what happens when I put in a half to the power of x. Aha, that's in the reverse order. But I guess that makes sense. If x goes up by 1 means you multiply by a half, bloop, bloop, it'll get smaller on this side. And dividing by a half is increasing on this side. So a less than 1. And we're not going to talk about what happens when it's negative because weird-ass things happen for non-whole x's when it's negative. So we're only going to consider the positive ones. So they tend to look like that. Okay? So that a is the number you multiply by when the x goes up by 1. Logarithmic functions are the opposite. Instead of changing the x by 1, multiplying by stuff, you have to multiply by x for it to go up by the same amount. And so it's going to take longer to go up. Desmos here is really clever. And it'll do log base 2. So log base 2 means that in order for it to go up by 1, you're going to have to increase, you're going to have to multiply by 2. So here we are at 0. If you want to multiply, if you want to make the answer go up by 1, you're going to have to multiply by 2. So times 2. And I'm going to times 2 again, and then it will go up by 1. And I'm going to times 2 again, and then it will go up by 1. Up to there. We times the 4 by 2, we got to 8, and it went up by 1 from where it was before. So it was at 2, 1. And then it was at 4, 1, 4, 2. And then we times 2 again, but we only add 1, and it's up there. And so it takes longer and longer and longer to go up by 1 each time. So just to remember, I'm just going to add something to this picture here. This one, when we add 1, that means we have to times by a. So over here on the logarithm function, it's the opposite way around. That's 1 there. And this is y equals log ax. And this time, in order to go up by 1, you're going to have to multiply by a. And technically this is the one for, if a is greater than 1. It is extremely rare to see someone write a logarithm with a number less than 1 in this position here, but not impossible. Okay, so that's what the graphs look like, and you can always do all the normal things that you do with graphs to shift things over. So I could, for example, say sketch the graph of y equals 2 to the x take 1 . No, I won't do a third. 3 times 2 to the x take 1. Okay, so we know what 2 to the x looks like. It will do that, and then when here it's 1, it will be at 2 there. Because when you go up by 1, you multiply by 2. Okay, and the next one will be 4, right? You go up by 1 again, and this time you'll times by 2 and you'll end up at 4. So these are the main points that it goes through. So that's y equals 2 to the power of x. But multiplying by 3 will multiply every y value by 3. So this 1 will go up to 3, right? It was at 1, and now I might have to fit a few more in. And now it's at 3. But it's still going to have the property, and so when I go up by 1, I'm still going to multiply by 3 because that's how the powers work. Multiply by 2, so it's going to go up to 6. Also, it works that the 2 gets multiplied by 6. And this is going to be 1.5. Okay. To the power of x. And finally, the graph we really want is 2 to the power of x take 1. Now I know if I put x take 1 into a spot of a formula, that will shift the graph forward by 1. So this thing here at 3 will actually happen here at 1. So all of those same graph moves that you can use to figure out what a graph is doing, you can do that for any graph you like, including exponential graphs. Okay. All right. Something you may notice about the logarithmic graph is that it doesn't have any points over here. And let me just see what the computer does when I try and do log 2 of -7. It says undefined. Okay. All right. Well, but what does that mean? Well, what that means is that when you, it always starts here to have 0 at 1. oh, can I do that? That's cool. And when you move, you know that in order to move down 1, you have to divide by 2. And in order to move down 1 again, you have to divide by 2 again. And so you're always going to be dividing by 2 as you move along the x-axis, so you're never going to quite get to 0. So your logarithms are never going to be equal to 0. All right, so some properties that are useful to know. We're up to how the rules work. Okay. Whoop. So the first rule is that we know one thing about this, is that the logarithms, first rule is that if you keep adding the same thing, you keep multiplying the same thing. Okay? When you do an exponential, and it's the reverse when you do a logarithm. So these are the original rules that are from the definitions. This is always multiplying the same thing. So what an exponential does is it turns addition into multiplication. And so we can actually create this new rule, some algebra rules, which are that a to the to the b plus c is the same as a to the b times a to the c. And a to the b minus c is the same as a to the b divided by a to the c. And these follow from the fact that you know that if you keep adding the same thing, you'll keep multiplying by the same thing. That comes from this rule here. You know that if you keep adding 1, you'll be multiplying by a, because that's the definition. And so if you add c lots of 1, then you'll do a c times, and that will be a to the power of c. And you also know that a to the power of b then to the power of c is the same as a to the power of b times c. So you'll notice that when addition up here in the power is multiplication down below, and subtraction up here in the power is division down here below, and powers of powers is multiplication. Okay, that's cool. Logarithms are the opposite. If you multiply inside, it becomes addition to the answer. So log base anything to the a times c and subtraction, division is subtraction, and powers is multiplication. So they do the opposite of each other. And these are our main rules. They're called the exponential laws and the log laws. Oh, one more rule. Anything to the 0 is 1, and log base b of 1 is 0. So these are called the exponential laws. And these are called the log laws. Okay, So I just want to point something out to you that's important to know about how logs and exponentials work. And it's where they fit in the order of operations. So the order of operations goes that you do plus and minus. They're the last things that you do. So if you see a plus, then you have to do everything else around it. The things that are nearby to the pluses have to be done before the pluses. And the minuses are at the same level as the plus. Times and divide, same deal. If there's a plus nearby to a times, then the times has to be done first. But they have to be done after the things higher up. Powers, that's how a calculator does powers. See, look at this, exponentials. 3 to the power of 6. It draws it with this caret symbol. So that's how I'm going to draw it here. And roots are higher up there. If there is a root with the times next to it, the root sort of has to happen first. And the only thing that you can do to override this order is to put brackets in. Brackets or a horizontal line will tend to hold things together as well to override the order. And you'll notice there's usually a horizontal line as part of the root symbol. Okay, so look at this. Look at what the exponentials do. In the exponentials, if there's a plus on the inside, it becomes a times on the outside. So with the exponential laws, and with the log laws, if there's a times on the inside, it becomes a plus on the outside. This helps some people to remember what's going on with these laws. And it can take a bit of practice to get used to it. So really I should do some work on this, but there is one more law that I want you to be really sure of. So 2 more laws. One is that if there's a plus on the inside of the log, there is literally nothing you can do. You're just going to have to do the addition and then do the log. But you definitely cannot split a log over a plus. And if there's a plus between these 2 powers, there is just nothing you can do. It's just really not much. You can try very hard to use all your normal algebra laws to fit with this. And you can. There are some tricks you can do to get a little of the way, but there is no simple rule for dealing with these things. So please don't. Almost nothing expands out over plus, just so you know. All right, one more law that is worth pointing out, and that is how these combine with each other. So there was the exponential laws on this side and the log laws on this side. So log base b of b to the a is just a. And b to the log base b of a is just a. What this means is that log base b is called the inverse of b to the power of a. If you do log base b of something, if you do b to the power of a and then you do log b of the answer, you will get a back. And if you do b to the power of log base b of a, if you do log base b of a and then you do b to the power of that, you'll get a back. And that's because they're the reverses of each other. Okay, an exponential function, if you keep adding to the x, you'll multiply by the y's, whereas a logarithm's the other way around. If you multiply the x's, you'll keep adding to the y's. And so if you feed the y into the x, they'll sort of cancel each other out and do the opposite of each other. So i.e. log base b of x and a to the x are inverses. So let's just use these algebra laws to do some stuff. Okay. So now that we've got the algebra laws down, we should be able to solve some equations or do some simplifying. let's simplify that. I haven't actually listed this law as under the rules of algebra. I'm sorry, but I really should have, shouldn't I? All right, sorry about that. Let's add that to the list. So, this is just what I'm thinking here. Okay, so also a times b to the c is a to the c times b to the c. And a divided by b to the c is a to the c over b to the c. All right. And just for completeness of sake, a to the b to the c is a to the bc. Okay, so if you have something in an operation inside a power like this in the base of the power, then the power can come along if these are multiplication and division. So powers only interact with times and divide when it's inside the base. When it's inside the exponent, then it only interacts with plus and times. Actually, this one should be written in the reverse, I guess. Like that. Yeah. Plus and minus and times on the inside becomes times and divide and multiply and powers on the outside. That's for exponentials. But plus and divide and powers on the inside of the base interact this way. And logs don't really have laws for that. We'll just have to figure them out from the log laws. Okay. So now let's do an example. Let's simplify 2 to the 4 times 3 to the minus 6. So 2 to the 4 times 3 to the power of minus 6 is 2 to the power of 4 times, I'll do it one step at a time. So there's a times inside this power which has minus 6 as an exponent. So exponents can come across multiplication. And then 2 to the 4 to the power of minus 6 is 2 to the minus 24. And that's 3 to the minus 6. And that's probably as simple as it's going to get. Yay! Not particularly edifying, but there you go. That's a wickedly small number. There is another trick that it's worth pointing out, that a negative power is the same as 1 over. Because it's 0 minus 24, right? So it would be 2 to the 0, which is 1 over 2 to the 24, and 3 to the 0, which is 1 over 3 to the 6. Which is a horrifyingly huge number. So this number is very, 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 very small. So we could do some simplifying with logs too. Log base 2 of 4 to the power of 8 times half to the power of 6. Let's see what happens when we do that. So, well, logarithms do turn times into plus, so we could deal with that. . And powers inside the log is multiplication on the outside, so I can bring the power out. Okay. What else have we got? Well, that's a division there, so we could totally use the rule for division on the inside. Is subtraction on the outside. And I know what log base 2 of 1 is. Log of 1 is always 0. Okay. Well, log base 2 of 2 to the anything should be that thing, because they cancel each other out. So that's the same as 2 to the power of 1, right? Oh, and 4 is 2 squared. Okay, so log base 2 of 2 squared, they sort of undo each other, so we get 2, and they undo each other, so we get 1. So we get 16 minus 6, so we get 10. Okay, it comes out to a neat whole number, which is how I set it up to begin with when I thought of the example. So I managed to use a whole lot of the log laws in order to do this simplification. And that's sort of what I'm getting at, that it's that we've got all these rules for how log interacts with stuff, and all these rules for how it interacts with powers and how it interacts with multiplication and division, and we can use them to figure out as simple possible answers as we can. But I do remember that I have missed one rule that I need to say, which is how do logs interact with logs. So there is one rule which allows us to convert one log to another. So we can say that log base b of a divided by log base b of c is the same as log base c of a. Okay, it's a change of base law for logs, it's called. And it matches most closely to, I don't know which one it goes with, but it is totally a thing that we can do. Okay, so we can use that law to be able to calculate what log base 2 of anything. Look, I'll get my calculator to do it. I can do log of 4 to the power of 8 times a half to the power of 6 divided by log of 2 because, and I get 10. So when you do log of something divided by log 2, that's the same as doing log base 2. And so you can get your calculator to do log base 2 if you know that rule. Okay. It would also work even with the ln because it doesn't matter what base it is. So let's just do one more try just to make sure that you believe me. 4 to the power of 8 times a half to the power of 6 divided by ln of 2, also 10. Doesn't matter which log you use, it will always work. Well, next would be attempting to solve equations using these relationships between the logs and exponentials and stuff. So here's an example. Uh, 3 to the power of 3x plus 1 equals 243. Okay, so my goal is to figure out what x is, right? I'm going to solve that. Solve. These are the instructions. So I would really like this x not to be up in the power. So I've got some options. I could do log base 3 on both sides, because log base 3 is the thing that cancels out 3 to the power of. I know that rule, and so I can do this. So I can take the equation I already have, and I can do this. So log base 3 and 3 to the power of cancel each other out. And this is whatever it's going to be. I could ask my calculator what that is. That would be ln of 243 divided by ln of 3. Which is 5. Cool. 243 must be 3 to the power of 5, if that's going to work. Because if this was 3 to the power of 5, they would cancel each other out to give me a 5. 3 to the power of 5 is 243. Oh, cool. I might even actually just do that working. Which is 5. And now it's an ordinary equation. I can subtract 1 from both parts, and I can divide both parts by 3. And I guess that makes sense, because 3 times 4/3 plus 1 is in back 3 to the 5, which is 243 according to what the calculator tells me. Nice. Let's do something that's a little bit trickier. No, first let me do this one, and then I'll change it to another number. Okay, e to the 3x plus e to the x is 0, apparently. Well, here's the thing. Did you see that graph earlier? The first graph when I did e to the power of x? Any positive number to the power of x can never be 0. Even if it gets really close to 0 over this side, it's never actually going to be actually equal to 0. If I zoom in far enough, I will find a gap between this line and the x-axis. And I'm not being very convincing here because it's not actually giving me anything good, is it? That's as far as I can zoom in. Oops, a day. Well. Desmos, it gets very small very quickly, but it's never equal to 0. And so I'm allowed to use the fact that it's never equal to 0 in order to calculate this. And so I should probably go back and add that to one of the rules. So one of the rules is for a positive, a to the x is always positive, no matter what x is. And also, log base b of x is only defined only for x positive. That's a useful thing to know as well. All right, well, our rules are getting a bit joined together, but we need them all. So if I'm going to solve this, I might notice that e to the anything is never 0, and e to the anything is never 0, and if I add two positive things, I can't make 0. E to the 3x is greater than 0, and e to the x is greater than 0, So therefore e to the 3x plus e to the x is greater than 0. So there's no solutions. What if I was solving this? What if it was a minus? That might possibly be equal to 0, because they're both positive, but you can subtract two positive numbers to get 0. So e to the 3x equals e to the x. If I add e to the power of x to both parts, I can get that. And I suppose I could, I don't really want there to be x's on both sides, so what if I divide by e to the x? But I know that when you subtract two powers, when you divide two powers of the same thing, you can subtract the powers. And so e to the 2x must be 1. And I can get rid of the e by doing ln, because ln is the opposite of e to the x. And so we get 2x equals ln 1, which is 0, and we divide by 0, we get x equals 0. Nice. What if it was something a little more crazy like this? I'm going to stick a minus here. So if that was a plus, there would be no solution. I'm adding three positive numbers and getting 0. So let's put it as a minus. Okay. Did I actually put the instruction to solve it? Yes. Okay. Right. This one's a bit trickier. When there's lots of bits and pieces added together and equal to 0, I normally attempt to factorize it. But I only really know how to do that if it's a quadratic equation. Well, this can be rewritten as a squared, right? Because when you multiply up here, you can do powers of powers. And now it is a quadratic equation. If this was x, I would attempt to factorize it like this. So I would have whatever that was, and I'd have to think of two things that multiply to give 2 and add to give minus 3. So minus 2 and minus 1. Okay, so either e to the x minus 1 equals 0, or e to the x minus 2 equals 0, because if you multiply two things to get 0, one of them has to be 0. So e to the x equals 1, or e to the x equals 2. So we do ln on both parts. So x equals 0, and ln on both parts. So x is ln 2. And I can't see any reason why we can't just leave it as ln 2. We can calculate what ln 2 is. It's about 0.693, but that's a horrifying decimal, so I'll just leave it as ln 2. So x is equal to 0 or ln 2. Can we just test it to see if that's going to work the way it should? E to the power of ln 2, 2 times ln 2. Minus 3 times e to the power of ln 2 plus 2 is saying 1.2 times 10 to the minus 12. That's pretty horrifyingly a small number. I reckon the calculator's having trouble rounding that off. And so I reckon that's approximately 0. Okay, and what happens if I put 0 in here? Okay, is coming out to properly 0 that time. Okay, so that works. Okay, so I've solved some equations that have got exponentials in them. What if I attempt to solve some equations that have logarithms in them? Okay, ln x plus 3 equals ln 2. Okay, well, adding 3 to the ln should correspond to multiplying the x by something. Yeah, I don't know what to do there. But I guess if I put the ln's together, I might have a chance. So let's give this a go. I could move the ln over there, and then they'll be together. And there's a log law. Subtraction between the logs is division on the inside. Let me just check that. Yep, outside minus is division inside. So we can go 3 is ln of 2 divided by x. And now we could get rid of that ln by doing e to the power of both sides. And so that's 3 is 2 on x. So now it's an ordinary equation. I can multiply by 2, multiply by x, and divide by 2. X is 2/3. No, it's not. Where'd the e go? That's an e to... That's still e cubed. Okay, so we get x is 2 divided by e cubed. All right. Well, I guess that's the best we can do. And I suppose if you put 2 divided by e cubed here, the division to subtraction rule would make it ln 2 minus ln e cubed, and the ln e cubed would be 3, and so everything will cancel out. Rightio. What about this one? All right, log 2 of x plus 1 plus log 2 of x minus 1 is 3. Okay, well the log laws say, let me just copy it, because if I had this in an assignment and I handed it in, I would actually rewrite the original equation on the page so the person marking it didn't have to go look up what the original was. Well, there's a log law that says that when we do addition between the logs, it's multiplication inside the logs. And I can get rid of a log 2 by doing 2 to the power of. Like that. And so they'll cancel and I'll get x plus 1, x minus 1 equals 8. Okay. That's not particularly helpful. I'm going to have to expand it all out to make a proper quadratic equation so that I can solve for x using like factorizing or the quadratic formula or something. So let's see, x times x is x squared. Oh, it's x plus 1, x minus 1. That's going to be x squared minus 1 squared. So So x squared minus 1 is 8. So x squared is 9. So x is plus or minus 3. Okay. Now there's this thing that happens with logs that I need to warn you about. See this thing here? This thing isn't defined when x plus 1 is negative. And this thing isn't defined when x minus 1 is negative. But this thing here, if x plus 1 and x minus 1 are both negative, then this is positive, and so this thing actually is defined. And so when you use those log laws on an equation, sometimes you get extra solutions that don't actually exist. Because they're a solution to this equation, but not to that equation. So we're going to have to substitute both of these back into the original equation to see if they work. So okay, so log 2 of 3 plus 1 of 3 minus 1 is log 2 of 4 plus log 2 of 2, and that's log 2 of 2 squared, and that's log 2 of 2 to the 1, which is 3, and that's correct. So that's x equals 3. X equals minus 3. Log 2 of minus 3 plus 1 is log 2 of minus 2, which is undefined. That doesn't exist. You're not allowed to do logarithms of a negative number. So that's it. Okay. So I've solved the quadratic equation. I've managed to be able to figure out how to solve this equation here using the log laws. Okay. So it usually turns out that one of these solutions works and the other one doesn't, but sometimes both of them work, and sometimes neither of them work. That's just the way it is. You're going to have to check them both because this move often introduces extra solutions. So I think we've got a pretty good handle on using these laws. If you need some extra practice, I would recommend just having a look at a textbook. It would have lots of practice at using these various laws here and solving equations and that sort of thing. Give them a try and see how they turn out. Something like the Khan Academy will have plenty of exercises on using log laws and exponential laws, and you can practice them there as well. Really, it takes a while to get fluent in it, just like you might learn an idea for how to do plurals in Hebrew, and it'll just take a while to be able to do it properly. Okay, so we've dealt with, what have we got? We've got what is it, what is the graph like, what rules are there for working with it. We've done algebra, now we should do some calculus. So basically, what rules derivatives. Now, the derivative of something is a picture of how quickly it changes when you change, move the x. So this thing here, if I move x by 1, then it changes by timesing by 2. So if I move x by 1, then the amount that it changes by is 2 times whatever it currently is. But of course, it's not really moving by 1. I need to know what happens when I move it by a very tiny amount. But it's the same general idea. An exponential function, if you move by a bit, then it'll be a multiple. The change should be a multiple of whatever the current value actually is. And so what happens is that the multiple it is, the reason why we are interested in the number e is that the multiple is 1. And so here's the rule. if y is equal to e to the power of x, then dy and dx is e to the power of x, which is like mind-boggling. It's very cool. And if it's not e and just is some other number, then it turns out that if y is equal to some number to the power of x, then dy on dx is some multiple of the current y value, which is also a to the power of x. And the correct multiple to pick is ln of a, which is really, really cool. So the reason we care so much about e to the x and ln x, just so you know, it stands for logarithm natural. The reason we care so much about them is actually because of calculus, because of the derivatives. They keep appearing when you do derivatives. If you want to do the derivative of 2 to the power of x, it turns out to be ln 2 times 2 to the power of x. And so it's really important to know what ln 2 is and how to do ln in order to calculate these things. So what happens when you differentiate a logarithm function? Well, a logarithm has the opposite property. If you multiply the input by a number, then that'll be adding the input, adding the output, adding something to the output. But that's not at all how derivatives work. We want to figure out what happens if you move the x forward by just a little. How much does the y change? And that's going to be a bit tricky to prove how this works. But we do know something. We know that if you increase that it takes longer and longer to change the value of y. Here we have to go from 10 to 1,000 in order to get from 1 to 2. And here we have to go from 100 to 100,000, which is from 10 to 100, which is 90. Here we're going to have to move by 900 to get up to the next one. And here we're going to have to move by 9,000 to get up to the next one. It takes longer and longer and longer to move up by a little bit more. So the slope, like the rate of change, is decreasing. It's getting smaller and smaller and smaller. It's never quite zero. It's getting smaller and smaller. And it turns out that the way it gets smaller is it's just 1 over the answer you have already. Which I guess kind of makes sense, I suppose. If the derivative of an exponential function is a multiple of what the current value is, so number times current value, maybe the derivative of a logarithm, being the opposite, should be number divided by current value, which it is. So if y equals ln x, then dy on dx is 1 over x. And that is just beautiful. It's amazing. And it is so cool. This is so cool that later on mathematicians define ln of x by being related to 1 on x. They start with 1 on x and use it to create ln x, which I think is really cool. They define ln x to be the function whose derivative is 1 on x, which is just fabulous. You may notice me doing something here. I didn't put brackets around that. Mathematicians can sometimes be a little bit lazy there, and it's a layover from some old kinds of mathematics, and they don't always put brackets around the thing next to the ln. So sometimes you won't see that there. So just be careful. But that's what it really means, and I will always just put the brackets in. Okay, so but David, what if it was log base b? Well, if you really want a rule for that, you can figure it out. But I know how to figure that out using the change of base law. but it's going to come out to this. It's going to be 1 over ln b times 1 over x. So these are the rules of how these functions differentiate. The only ones you actually have to remember, just for future reference, are these ones, because you can get the other ones from the laws and from the rules for how differentiation works. Okay. So don't forget you can combine them with the other rules for differentiation. Like the product rule and the chain rule and that sort of thing. So let's give it a go. We'll do lots of examples of how to do derivatives of these things. So I did have a list here of some possible problems to try. All right. So f of x is going to be x. Now, I'm not going to give it a name. Let's call it x squared e to the 4x plus 1. And we'll do one with an ln in it, say. Let's do that one. And 6 to the 7x and one more log base 2 of 5x. All right, let's do all these derivatives. So A, we'll call it f of x so that it will be easier to do this. Now, because it's made of two things multiplied together, I'm going to have to use the product rule. So I'll do the derivative of the 2x, of the x squared, which is 2x, and I'll keep the e to the 4x plus 1. And I'll do keep the x squared, and I'll do the derivative of this, which is the same as what it was. But then because of the chain rule, I'll have to multiply by the derivative of that, which is 4. And so I get 2x e to the 4x plus 1 plus 4x squared e to the 4x plus 1, which we can totally just write like this if we really wanted. They've both got an e to the 4x plus 1, and it's tradition to bring them together. Okay? Actually, I'm just going to, in just a minute, I'll try and remember that I have something else to add to this page over here, this page with the derivatives. It's going to be important. Okay, well, the rules say that I should be able to do the derivative of this by, the chain rule's got something inside it. It should be 1 over whatever that is times the derivative of that. So, well, let's just go for it. The derivative is So I can't just say equals, so I have to say the derivative is. It should be 1 over this times whatever the derivative of this is, because of the chain rule. Okay. Well, this thing is what I get when I do this. 1 over a fraction is the fraction up the other way. And I'll just hold off doing this derivative for a minute. And it seems to me that a derivative of a fraction, I could use the quotient rule for that. I might put brackets around this because it's going to get a bit crazy. So the derivative, how does this work? We do the bottom squared on the bottom, keep the bottom, do the derivative of the top, which is 1, minus, keep the top and differentiate the bottom. Bottom is also 1. Okay. What have we got on the top there? We've got x minus 5 minus 2 minus x. X minus 5 squared. Beautiful. Minus 7. Okay. Oh, and I guess that cancels with that. So we get minus 7 over 2 plus x times x minus 5. What an interesting answer. Wow. That's kind of cool. Cool. Not what I was expecting, but there it is. No point expanding out a denominator. If you really feel comfortable, you could put it at x plus 2 first. Okay. There is an alternative way of doing this, which uses the log laws. But in order to use it properly, I'm going to need to tell you one more rule for differentiating logs. So it's all well and good to be able to do ln of x. But if I asked you to find a function whose derivative was 1 over x, you could actually find another function which would be ln of minus x. And you're saying, David, didn't you say that you couldn't put a negative into ln? Well, minus x doesn't have to be negative. It could be positive. If x was negative, ln of minus 3 would be ln of plus 3, and that'd be okay. And the thing is that if you do minus x when it's negative and ordinary x when it's positive, that's the same as doing the absolute value. And so we can actually do this. If y is ln of the absolute value of x, which we do so that we can sub in a negative number inside it, then dy on dx comes out to be also 1 over x. So this answer isn't any different when x is positive, right? If x is positive, then the absolute value of x is the same as x. But if x is a negative number, it'll be 1 over whatever x is, which would be a negative number. And so this is a really cool thing here that will allow us to do some neat tricks with what I'm about to do here. So, or, was it 2 plus x on x minus 5? Okay. So if this function is defined, then that's the same as this answer. So remember how we had this issue that when you pulled ln's apart and put them together, there were times when it was defined and not defined? Yeah, that's an issue. So my log laws tell me that this should be this. Okay? And that'll be okay as long as the 2 plus x and the x minus 5 are positive. But the problem is they're not necessarily. If 2 plus x and x minus 5 are both negative, then this derivative will be actually, this calculation will actually be possible, and I'll be able to do it. Let me go to the computer. All right, well, that's what ln of that looks like, which is fine. And it's got this giant gap here between 5 and minus 2, which sort of makes sense. But look at this function. This function only has this red bit. It doesn't have this black bit. It's not defined in as many places as the other one is defined. So that's annoying. So I'm going to have to do something about that. If it's defined, if this is defined, then whatever this thing is here is positive. And so I'm going to do the following. That's equal to ln of the absolute value of 2 plus x over x minus 5 when it's defined. Because when it's defined, that thing's positive, so it's equal to its absolute value. And that's the same as this. And this I can split. And the derivative of that I can totally do. It's 1 over 2 plus x times the derivative of the 2 plus x because of the chain rule. And it's 1 over x take 5 times the derivative of the x take 5 because of the chain rule. And the absolute values disappear because I don't need them afterwards, because if that number's negative, it will need to be a negative derivative. And so I could put it over a common denominator if I wanted, just to see if it comes out to the same answer. So let's see, this is x minus 5 over 2 plus x minus 5, and this is x minus 2 over, sorry, not x minus 2, 2 plus x over 2 plus x minus 5. And so I've got x minus 5 minus 2 minus another x, which is minus 7 over 2 plus x minus 5. So it's the same answer as the other one, ever so slightly less work and less stuff that could go wrong. Okay. Beautiful. That's some derivatives that I can do. Let me just look at my list of what I was going to talk about. So I could use derivatives to do all the things that I used to do with derivatives, which means I could calculate rates of change, and I could do second derivatives, and I could do I could find the equations of tangents. All of that are things that I can now do. So let me just do one more example here. What if I had a function that had some letters in it and you didn't tell me what they were, right? And so I went, what if y is equal to c over 1 plus a e to the minus kt for c and a and k being positive. Okay. And then just a second. And t is greater than 0 as well. So these are constants. Okay, so we're saying that this and this and this are constants, and the t is the variable. Find the value of y at the inflection point. Okay. So to do an inflection point, I'm going to need to know where it's the second derivative is positive and negative. In which case I'm going to need yes, that's what I'm going to need to know. So I'm going to need to find where it's concave up and concave down, which means I'm going to need to find the second derivative. So y was equal to c, and I'm going to rewrite it like this because it's going to be easier to do. So dy on dx. The c is a constant multiplied on it will still be there. The derivative of this would be minus 1 thing to the minus 2. But I'm going to need to do the derivative of this. The derivative of the 1 is 0. A is a constant multiplied on. The derivative of e to the anything is the same as it was before, and because of the chain rule, I'll have to multiply by the derivative of that thing, which is minus k. And so let's just figure that out. That minus will cancel with that. We'll get a k. We've got an a. We've got a c. We've got an e to the minus kt. We've got a 1 plus a e to the minus kt to the minus 2. And so now I have to do the second derivative. D squared y and dx squared, which, okay, let's see. I've got two things here. They've both got an e in them, so I'll have to do them separately, and I'll do the product rule. So the derivative of this is k a c e to the minus multiplied on. The derivative of e to the minus kt is e to the minus kt, and then I'll have to multiply by the minus k, and then we keep this bit. Okay, and then because of the product rule, we'll keep this bit, and then we'll differentiate this bit, which would be minus 2, 1 plus a e to the minus kt to the minus 3 times, because of the product rule, the derivative of the inside, but we've already figured out what that is. We did that earlier, so I'm just going to copy that bit. Okay, it's complicated. Whoa. Okay, so let me just say we've got a minus k squared ac e to the kt minus kt, 1 plus a e to the minus kt to the minus 2, and we've got a 2, we've got a minus minus, we've got a k squared, we've got an a squared, we've got a c, we've got an e to the minus kt squared, and we've got a 1 plus a e to the minus kt to the minus 3. All right, so let's see if we can pull out all the things that are in common here. We've got a k squared in both of them. We've got 1a in both. We've got a c in both. We've got an e to the minus kt in both. We've got a 1 plus a e to the minus kt to the minus 2 in both. Okay, and that is going to be times, what have we got left here? We've got a minus, and that's it, minus 1. And over here we've got a 2a e to the minus kt and a 1 plus a e to the minus kt to the minus 1. Oh, wow. That doesn't look fun. Okay, so I'm going to need to find when this is 0. So, so k squared a c e to the minus kt 1 plus a e to the minus kt to the minus 2 times 2a e to the minus kt 1 plus a e to the minus kt to the minus 1 is 0. And none of these are allowed to be 0. And this could be 0, though it can't really, can it? because it's 1 over something, and 1 over something can never be 0. It can never be 0. It's either undefined if the bottom is 0, or it's just 1 divided by something that it's a positive or negative number. It's never 0, and so it's just this that's 0. So therefore, 2a e to the minus kt 1 plus a e to the minus kt to the negative 1 minus 1 equals 0, since e to the minus kt and 1 plus a e to the minus kt to the minus 2 can't be 0. Okay. So 2a e to the minus kt 1 plus a e to the minus kt to the negative 1 equals 1. If I multiply both sides by that, it'll go away. Because it's currently to the power of minus 1. Sorry, I've been working off the screen this whole time. Sorry. When I got to the derivative, I noticed that these things were here. I got rid of them because they're not allowed to be 0 anyway. And then I'm starting to put the 1 over here, multiply by this thing because it's currently 1 over that. So multiply it to make it go away. I can see an a e to the kt, which I could subtract from both sides, so I'm going to get a e to the minus kt equals 1. Okay, so e to the minus kt equals 1 over a. Okay. Actually, do you know what? That's a negative power. Why don't I multiply both sides by it? A equals e to the kt. And the c is neatly gone away. So I need to get rid of that. So I can do ln a equals ln e to the kt. So ln of a is kt. And so t must be 1 over k ln a. Right. Well. Whew. All right. So I'm going to need to know whether the derivative is positive or negative on either side of that. So this is t, this is d squared y on dx squared. So it's a sign diagram for d squared y on dx squared. Here is 1 over k ln a. There's 0. Okay. Well, kt is ln a, right? Minus kt would be ln of 1 over a, which is interesting. In fact, actually, a e to the minus kt, when I did my working, where'd it go? A e to the minus kt is 1, right? So if t is even bigger, I'll be having e to the minus k even bigger number, which would be a e to the kt even bigger. So just let me just a second. That's equal to a over e to the kt. So if t is greater than 1 over k ln a, then e to the kt is greater than e to the ln a, which is a. And so therefore a over e to the kt. So if I divide by a by something bigger than a, it's going to be less than 1. So if that's less than 1, then back here, when I calculate this derivative here, that's going to be less than 2, which means if I go to the minus 1, it'll be greater than 2, greater than a half. Ugh. So a e to the minus kt is less than 1. So 1 plus a e to the minus kt is less than 2, which means 1 plus a e to the minus kt to the negative 1 is greater than a half. So if you divide by something less than 2, the answer's got to be more than what you get when you divide by 2. And so uh, 2a e to the minus kt, 1 plus e to the a e to the minus kt to the minus 1 is going to be greater than 2a e to the minus kt times a half, which is greater than 1, which is not greater than 1. Oh, poo. I'm annoyed. Okay, look. Let's just imagine if t gets extremely large, then this number is approximately 0, and so I'm going to get a negative 1. Right? And that's approximately 0, and therefore d squared y on dx squared is going to be this bit is going to be negative. Which is negative. And then if t is very close, if t is close to 0, then e to the minus kt is approximately e to the 0, which is 1. And so I get 1 here divided by 1 plus a, and the 1 plus a is not that far from a, and so we've got plus 2 times a, which is positive. I reckon it's going to come out to positive. I reckon I should have said way back here that a was greater than 1 in order for this thing to work. K is greater than 0 and c and a are greater than 1. Sorry, because then if a is greater than 1, then we get that here, my second derivative, we get that's greater than 2. We get something bigger than 2, and so we get a positive number. Okay, so it really is an inflection point because the concavity changes. Is an inflection point, and we want to know what the y value is at that point. So let's see. And here at t equals 1 on k ln a, we've already discovered that at that point, so y is equal to c over 1 plus a e to the minus kt, which is c over 1 plus a e to the minus k 1 on k ln a, which is c over 1 plus a e to the minus ln a, which is c over 1 plus a over e to the ln a, which is c over 1 plus a over a, because e to the ln a is 0, is a, because they cancel each other out, which is c over 1 plus 1, which is c over 2. Beautiful. Right. We could technically have not checked if it was a proper inflection point we could probably have skipped the bit where we calculated what the second derivative was on either side here, because we were told there was an inflection point. So assuming that there really is an inflection point, it would happen when the second derivative was 0, and we could probably have said that. We probably could have said, since the second derivative is 0 and you told me there was an inflection point, that must be the inflection point. So we could have done that. Okay, one final thing. What is it used for? It's used for situations, exponential and exponential functions are used for situations when things grow, population or other things have growth and decay. It's used for growth and decay situations. So, for example, population of bacteria decay of radioactive elements. It's used for the process of to model the process that the body uses to when it uses up medicine. They tend to appear in all of those situations. Now, some of these functions are more. It's also in compound interest. In finance. In any situation where you have something that keeps on getting bigger and bigger based on how much it already has, or keeps on getting smaller and smaller based on how much it already has, that's when these things tend to appear. So one of these examples in particular is called the logistic model, which is a model of how populations grow when there is a limit to how far they can grow. So two possibilities are unbounded population growth, such as that's y is some constant e to the kt usually. Where, the population keeps growing like that, and normally time moves forwards from 0. It keeps going like that. Or you could have logistic population growth, which is, population growth with a capacity. And it's called logistic. The logistic model. And that tends to look like this. like that. And the equation that I just used to do that fancy thing with the inflection point happening at C on 2, that was based on this model here. And this model tends to have formulas like this. Y is equal to C over 1 plus A e to the minus kt for C and A greater than 1 and k greater than 0. It's called the logistic model. So when k is equal to, when t is equal to 0, you get c over 1 plus a, which is what you get at this spot here. And when t is extremely large, you get c over 1. So as t goes towards infinity, e to the minus kt goes to 0, and so therefore y goes to c over 1 plus a times 0, which is c. And so you can never get to c, but you can get pretty close, and you can never get above c. Okay, the function never goes above c. It is actually possible to have logistic decline in population as well, but this will do for the moment. C actually has to be more than 1 plus a for this to work. Well, more than c over 1 plus a, whatever that is, which it must be. Goes above c, and c is called the carrying capacity . All right, so the last kind of example you might have is attempting to solve a problem using the carrying capacity. So a population of bacteria in a bottle of milk grew according to a logistic model with population P at time t given by p equals 900 (900 plus 1 over 900 over 1 plus 17 e to the minus 0.8 t, where p is in billions of bacteria and t is in hours. All right. Cool. How long until reaches 800 billion bacteria? Okay, So the first thing I'm going to notice is that the carrying capacity is 900, because that's the position the carrying capacity goes in this formula. And so since 800 is less than 900, it is possible to reach it. Is less than the carrying capacity, it is possible to reach 800 billion. Okay, good. It's a good start. I guess technically I should figure out what it is at 0, because if 800 is less than what it started with, then it won't be reaching that either. So we should just check that. At t equals 0, p equals 900 over 1 plus 17 e to the minus 0.8 times 0, which is 900 over 1 plus 17. Now e to the 0 is 1, which is 900 over 18. That'd be 50, wouldn't it? So 900 over 9 would be 100, and then another 2. Okay. Since 800 is greater than 50, it is possible. Okay, we need to know both of those bits of information, or even if it was less than 50, it's supposed to be a growing population. It's not going to get to 50. Okay, so that's great. 800 is between what it starts with and the maximum it can possibly get, so it must be possible to get to 800, and so now I'm going to solve the equation. So let's see. Solve p equals 800, which would be 900 over 1 plus 17 e to the minus 0.8 t equals 800. Okay, well, I guess it's really annoying that this is on the bottom. So if I multiply everything by that, I should be able to remove it from the bottom. And then if I divide by 800, that'll go away. So 900 over 800. Beautiful. And then if, I guess the hundreds will cancel, so that'll be 9/8. All right. So if I subtract 1 from both sides, 9/8 is 1 and an 1/8, so that'll be an 1/8. Beautiful. And then if I divide everything by 17, that'll be unwrapping even more things from this t. So whatever that is. Okay. Well, I guess I need to pull this out of the power, so I could do ln on both sides. But I don't feel comfortable with that right now. This is e to the minus something, which is already 1 over something. And so if I did 1 over both sides, I should be able to get this. So that's called doing the reciprocal. Now that feels more comfortable. ln of 8 times 17 is ln of e to the 0.8 t. And so ln of 8 times 17 is 0.8 t. And so I could divide everything by 0.8. So ln of 8 times 17 over 0.8 is t. And so t is approximately whatever that works out to be. Let's see. ln 8 times 17 divided by 0.8. Really? Eight times 17. Oh yeah, that's not a very big number at all. 6.14. So population reaches 800 billion at t equals 6 point, how many hours? 6. Yeah, well, I'm just going to go 6.14 hours. Beautiful. And that's enough. I'm going to stop there. Thanks for listening. Good luck.